Hey, this is the second part of chapter 4, and I'm going to focus on more of these Lewis structures. We'll say a few things along the way too about them, but generally we're just going to be talking more Lewis structures. The lab this week also covers Lewis structures, so hopefully by the end of the week before spring break you'll be in a great place with respect to Lewis structures. So this is the first part that we did last week. We got all these guys filled in. Something that I added that we hadn't done before was we talked about how right here the bond angles. So like a linear molecule, if you look at the linear, it's just, like a straight line. Even if you have 3 molecules, it just looks like a straight line. So this bond angle right there, that one's going to be 180 degrees. And that's all there is in something linear. So that's why we have 180 and 180. And then trigonal planar is something that has 3 groups on it. If you didn't catch it as we went along, these different names. The electron geometry is the easy, and this has to do with the number of electron regions. So it's like where the electrons are. So like right here, that one has 2 regions, whereas this guy has 1, 2, 3 regions. So 2 versus 3. So if it's got only 2 regions, again, it's linear, and it's going to have that 180 degree bond angle. Now the trigonal planar, we've got an atom in the middle, and then we've got some things that are kind of equally spaced coming off of him. And this is all in one plane, so like you can imagine it laying flat on the screen. This is all in one plane. When we did this in class, we had the models, and everyone got to hold the models and kind of manipulate them to help them. So this is, imagine like this is your circle, so that's 360 degrees. So one of these bond angles right there, it's 360 divided by 3, and you're going to have it being 120, which is what we've got right here, the 120. Triangle, trigonal, you can imagine like, see, that looks kind of like a triangle. That's why we use the word trigonal. Now tetrahedral is harder to see. This is a 3D shape. It's not flat. Over here it kind of looks like it's flat, but it's not a flat shape at all. So you could think of like 2 bonds of it being in the plane of the board, and then like this is jutting out at you, like it's like gonna hit you in the face, and then this is what's gonna be like hidden and going behind the screen. Now, I don't know if that's a great thing. If not, come in, grab some models. I've got some you can look through to make sure that you understand this. This bond angle here is 109.5. You might just want to memorize it to get a sense for it. It's kind of like a pyramid with a top, kind of, is how it looks. That's what we got there. Now, if you've got a lone pair, and I would recommend putting the lone pair at the top to be able to see this better. So lone pair. And then we've got our nitrogen. And this is coming from the nitrogen. Again, one of these is coming out at you, and then like this one over here is going like behind your computer screen, sticking out opposite of your computer screen. So it's 3-dimensional, so this makes kind of like a triangle shape, kind of. You can kind of see that triangle shape to it. It makes that triangle shape, so it's a triangle pyramidal. And you still have the same angles that he came from. So this is like the family name, or I told people in class like kingdom, phylum, genus, species. So like you could think of this as like the kingdom, and then like the molecular geometry is kind of sort of like the phylum in a way, or some lower level. So it's like the main category is the family, and then molecular is a clearer way of describing the shape. So the reason that all 3 of these are tetrahedral is because they all have 4 regions. You can see them highlighted. So they all have that same basic shape. So they all have the 109.5. But the reason this has a less than sign is that the lone pairs, we draw them as though they're like still, but actually they're like going like crazy all over the place. And they start pushing on the bonds that are near them. Let me kind of clean that up a little. So they're going to, they're going to kind of act crazy, and they're going to be pushing a little on these bonds and kind of squishing them in towards each other. Just a little. Like it's actually like 107, so it's not that much of a difference. It makes a little difference. So this is just a little bit less than 109.5. And then the same thing happens for water. The water Now these two are flat. This is a flat guy in the plane of the board. That's flat. And again, these electrons are kind of pushing on them. Again, it only goes to like 104.5, so it doesn't change a lot, but we just use a less than sign to show that the electrons are doing something. So that was one thing that I added to this list. And then I also had added the idea about these groups and reminded everyone about the electron geometry, what it was talking about. From this point on, you do all of these the same way that we did them up here. So if you are having a struggle with your valence, just make sure and practice it some more. So these are all the answers for the valence electrons. All right, here we have kind of a grouping. So that's one group. Notice they all have 4 areas. So 1, 2, 3, 4. I'm sorry, I meant to say 5 areas. And this is 1, 2, 3, 4, 5. I meant to be using the highlighter with that. I'm hoping everyone's getting the sense of it though. Like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So all of them have 5. 5 is what trigonal pyramidal matches up with. This one's really hard to see at first. I've kind of got an example here. So if you imagine that you've got a vertical axis, we call that axial. So the vertical is purple, and then the red part, it's kind of like what it does is it makes like a little triangle. So if you can kind of imagine like a triangle laying flat, like perpendicular to the board that you're looking at. That's a triangle. So this edge of it's kind of coming out at you, and then that back edge is kind of going back away from you, like a Y maybe. You can think of it like a sideways Y where the Y is sticking up at you. That's that shape. And this is the key thing, is that we're going to be replacing the bonds in this guy or this kind of shape with electron pairs. You want to start replacing equatorial first. So you're going to start in the red positions when you start doing the replacement. So for this one right here, it'll kind of look like that. I made it probably a little big. And right here is where those lone pairs are. So like you've lost the guy on the right. So like this is kind of coming out at the board at you. And if you turn it sideways on the screen, like if you put your head sideways, you could put a little kid on this side and you could put a little kid on this side. And that's why we call it a seesaw shape, is it looks like a seesaw that could go back and forth. That's called trigonal. I'm sorry, it's called seesaw, but all of these are in the trigonal bipyramidal family. So that's all in that family. And we're going to do another set of lone pairs. So again, I'm going to keep that vertical right here. And again, my lone pair goes equatorial. So I've got a pair here. They're so small you don't pick them up like on like a lot of spectroscopy. Like we're not trying to pay attention to the electrons, just the atoms. So in this case, this guy, I've just got the one that's coming out like this. And again, if you put your head sideways, it looks like a letter T. And that's why we call it T-shaped. Now between the two of these, or all of these, wait, I've got one last one, and then we'll do it. So then the last one, we've got the vertical. And notice we've got, this one had the lone pairs. Notice we've got a lone pair here, a lone pair here, and a lone pair here. So notice we're only seeing the vertical. Like that would be the fluorine, and the xenon is in the middle. So the reason that we have the bond angles with this one is that triangle, if I look, so I'm going to make it so that the triangle up here, I'm going to draw it so that I'm looking straight at it. So for example, this is the axis that's going up and down, so the axis is coming towards me, and then here's my actual bonds. So I've got a bond there, and a bond there, and a bond there. So if you're looking on, like your eye is like looking this way, you can still see that you've got the 120-degree angles. Kind of like earlier when we had this guy, it's like that. You're looking at that, except that this has an axis with some stuff stuck on it. So we definitely have the 120-degree angle. And you notice like on the second shape, we still have some of that angle. It's like we have this guy, but We're just missing one. So we still have a 120 on this side. But when we lose another one, now we don't have any 120s. They're gone. That's why this section right here has no 120s. And this one has no 120s. And don't forget that we also have the distance like from the purple to this red, and that's a 90. If you have the structures, you can really see it. And the purple to the purple is the 180. So that's why we have all those angles. This one right here, we still have the 90, the 180. I mentioned we don't have the 120. And for this one, we have the 180. And he's linear. You've seen this name before. There's a few names that repeat. Linear and bent, those are both some that repeat. So you'll see that name in different places. We don't overly stress about what the electron pairs are doing in that situation and whether or not they're making this bond just slightly less than 120. We don't stress about that one. It's just the tetrahedral and the ones on the other pages that we stress a little bit. So see, less than, less than. And then we have our final grouping. It's right here. So I've got a picture down here of an octahedral, and if you want to kind of think through the difference, so down here is the octahedral, and if you look up here, that's the trigonal bipyramidal. I don't know if I said why it was trigonal bipyramidal. The reason we call it a trigonal bipyramidal is because you can imagine this part making a pyramid, and then you can imagine like the lower part making a pyramid. So bi, two pyramids, trigonal because it has, each pyramid has a triangle base going on right there. All right, so now we have our octahedral. And again, keep that vertical axis going on. But now what we have basically is these purple pieces. So like this one is coming out at me, and this one's coming out at me from the board. And then the back ones are like going behind your screen. What you're looking at, they're like, they're sticking out behind it. And the reason we call it octahedral is not because it has 8 things on it, because it doesn't, it has 6. It's because it has 8 faces. If you imagine this like being filled in like a diamond shape, there's 4 faces on the bottom, and then there's 4 faces on the top. That's why it's called octahedral. Octahedral and tetrahedral are named the same way. They do some important stuff, and so I think that they were categorized kind of like at the same time, and that's why those have those names. Okay, so octahedral, we've got our sulfur, we're filling in all of our fluorines. The shape here, the reason that we have the 180 and the 90 is the red, from red to red, that would give you your 180. And again, if I'm going to look down this bond, and I'm going to make it red right there, this angle is 90. And this angle is 90, this one is 90, that's 90. So that's where we get the 90 from right here. Okay, so octahedral, you can actually put the lone pairs anywhere, but if you want to be able to really see the picture and have it make sense, you should put them axial. So here's what I'm going to do. I'm going to do it for this guy right here. So I've got one axial. I'm going to put my lone pair on the bottom, so I'm going to put my lone pair down there. And I've still got my purples. That's kind of like a square that's kind of coming out me, so that's like a square shape. So the reason I get square pyramidal is it has a square base, and then if you imagine it going up to the top, it looks like a pyramid. So square pyramid. Still have my 180s and my 90s. And then the last case, I'm going to put my second pair of lone pairs up in the top position. So all I have left is the purple. Kind of like that. It's got the red in the center for the axis, but the lone pairs are here and here. Remember, they're moving around like crazy. Again, this part right here, it's in a plane. It's like a square or rectangular plane. And this word right here should say square planar. And we got the 90 and the 180. If you're wondering how we get to these shapes, I'll go back through that really quick over here. So for these guys right here, you want to put this guy in the middle, 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 and this guy in the middle. And then we put the other ones around the outside. Tells you how many there are. You write them around the outside and you draw your bonds to them. Then you fill in the outer guys. So I'm going to fill in all of these. I'm filling in all of those, all of those, all of those, all of those. And then I count them. And when I count them, I get 40, which matches with this 40. So that means that that's a good structure. I do the same thing here. And when I count, that lone pair wouldn't have been in there yet. So right there, let me erase it for a second. This is what I get when I fill everything up. I've got my sulfur, I got my bonds to the fluorines, and the fluorines are filled up. Sulfur's okay, he's at 8. And when I count that, I get 32. So I actually have 2 more electrons to work with, a pair. So you just stick them on the central atom. And they get counted as a region. And again, this next case, when you originally draw him, you draw your fluorines, you've got the bonds of the fluorine, and you need a lone pair on the chlorine to make it have 8. So everyone has 8. When I count that, I get 26. I should have 28, so I've got 2 extra electrons that I can put in, so I just put on there. And then this last situation over here. So my fluorines have 8. I've got my bonds of my fluorines, and I got to give the xenon 2. When I add that all up, that's because he's got to have 8. That gives me 20. So I got 2 extras, and again, I just throw it on that central atom. But it's 5 regions, so it's in the trigonal bipyramidal family, linear 180. And just as we review this one, right here, he originally didn't have that set. When I filled in, I drew all my fluorines, I drew bonds to all my fluorines, filled in the fluorines. Notice that bromine has 5 things attached, but that's okay because it's in the expanded octet, and you can do that. You can also call that hypervalent, by the way. And then we go over and we count them up. We get 40, but we're supposed to have 42. So that means that we need 2. So you can just stick it wherever. Make sure it's on the central atom, but on any section of it. And then last but not least, we have this guy. And when you first draw it, you're going to draw it with all the bonds. Fill in your outer things. Make sure xenon has 8 at this point. And when you do that, it's 32. So since I'm supposed to have 36, I can put 2 lone pairs. You can put them opposite or near each other or something. Just don't put them like on the bond. You can put them around. That's how you get these higher structures. Now, none of these have anything to do with single or double bonds. I mean, triple bonds or double bonds. So I've got some examples of that one and this one. Oops, I just repeated. Here we go. All right, so this is the other set right here. So with this one, I pointed out something. This CH3OH, most molecules have more than one center, and that's okay. You draw the left and the right. If I had tried to draw this with everything on it, like it wouldn't have worked because my carbon isn't allowed to have 5 bonds. Not allowed. Carbon has to only have 4 bonds, which is 8 electrons. But we do this thing, especially you'll see it in organic chemistry, where things get grouped with hydrogens after them. So this is the grouping right there. So I've got 2 centers to this molecule. I've got the carbon and the oxygen. And I've got the 3 hydrogens that go on the carbon, and I've got the 1 hydrogen that goes on the oxygen. So I've kind of colored these in with 2 separate colors. You can see that the green has 8, so 2, 4, 6, 8. So that's 8 electrons on the left side. And then we already counted this bond here, so we're not counting that again. 2, 4, 6. So we've got 6 on the OH side. That gives me my total of 14, so my numbers match up. And because there's 2 centers, you have to say that the carbon is tetrahedral, meaning it's got a bond, and there's 4 of them, no lone pairs. And the oxygen is also tetrahedral when we're talking about the electron geometry. Remember, that's like the family geometry. It just means that he has 4 regions of electrons that are filled up. And then for the molecular geometry right here, our carbon is tetrahedral, but our oxygen is bent. That's that name that better describes what's going on. Our angle is 109.5, and the oxygen is 109.5, but we put a less than sign because the lone pairs over in this area are going to be affecting the angle, this angle right here. All right, so just want to be aware that you could have two centers. Another thing, this molecule is in here just because it has a positive charge. Want to make sure you got that one. Nitrogen has 5, hydrogen is 1 times 4, which is 9, but because we have a positive charge, we're removing an electron. That's why we have 8. The rest of it's pretty straightforward. You put brackets because it has a charge. You call it tetrahedral because it has 4 regions, and you still call it tetrahedral because it's got 4 regions. And the only time that this isn't the same is when you have lone pairs. All right, so then this is where we're going to start looking at some of the double bond things right here. So right here I've got oxygen and oxygen, and when I originally drew him, I drew him with one line, and I originally had another pair of electrons on either part of that oxygen. And when you do it this way, you end up with 2, 4, 6, 8, 10, 12, 14. So you end up with 14 electrons, but you're supposed to have 12. So when that happens, this is different than before, because before our real count was higher than the number we came out with. Now it's lower. So there we go. We put a second line, and each line represents 2 electrons. So there's a total of 4 electrons in there. And then 6, 8, 10, 12. The shape is just linear because it's got 2 things. Doesn't have any electron pairs, so he's still just called linear, and his bonds are 180. We talked about that earlier. Okay, so now let's look at what's going on with this fellow. So the first thing I want you to pay attention to is actually what I've X'd out right here, because this is the first thing that I drew. So nitrogen in the middle, oxygen's on the outside. Notice that nitrogen, he needed his lone pairs right there. It might not look like 2. I'll make it look like he's got 2. So 1, 2. When we counted this guy, I had 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. The problem is that I only had 24 allowed, so that means you have to make a double bond. And so I drew this structure right here as the first example. If you add him up, you're going to get that nitrogen has got his 8 electrons, so he's good to go. And we could say 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that structure works. So then I took a minute and I asked everyone, okay, so what's the question? Tell me the question. And they spoke up and said, well, why does the double bond have to be here? Well, it doesn't. You can redraw the same structure with your double bond here or your double bond here. And then we're going to put our electrons in. So this is what you get every single time that you write it. Now, this structure also has a negative charge. So you also would put brackets, I'm going to put it around the correct one. You would have brackets around the left one. I might have to kind of erase a few things to get it so that you can see it. I'm going to erase this part here for a second. So bracket, bracket, negative. Bracket, bracket, negative. Bracket, bracket, negative. So it's kind of messy right there. And when you do this, we say that it's resonant and that it's got 3 structures. So we have more information to say about resonant structures. We covered it with the 11 a.m., but we didn't quite cover it with the 9:30. So I'll put that in the next section, like the next week's. So not next week's, Thursdays. Here's the other thing you should know is that when you have double bonds, it's still just counted as a region. That is 1 region, 2 region, 3 regions. And that's why this is labeled, because of 3 regions, as trigonal planar. Notice there's no lone pairs, and so this guy is also labeled trigonal planar. Bond angles for anything trigonal planar is 120. And we did that upper structure, and I know it's a little messy. I've got a neater thing below. This was in contrast to this next structure. So if you look first at this one right here, this was the original. So put the carbon in the middle, filled it all in. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 electrons. That's too many because it says 16. And you may have noticed this or you may not have, but like this is a difference of 4, which is 2 pairs. So 2 pairs of electrons. That's going to mean that I'm going to need 2 double bonds. Or 1 triple. If I just had 1 pair of electrons difference, then I'm just going to need 1 double bond. Just as a little note. So we went ahead and we tried it like this. Fill in all your electrons, and it actually does work. You count them up, you get 2, 4, 6, 8, 10, 12, 14, 16. So you get 16, which matches with the 16 that you're supposed to have. Now this is considered 1 electron region and 2 total electron regions. Anytime you have 2, it's called linear. And again, no lone pairs on that central atom, so still linear. And we have just the tiniest bit left. So on this fellow right here, this is O3. You'll notice that O3, this is the structure, this is the cross-out structure. But when you do it, and you put everything on, make sure you don't forget the electrons on the central atom. When you count these guys up, you get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. The problem is that you're only supposed to have 16. So we need 1 double bond, because notice it's a difference of 1 lone pair. And make sure that you're rearranging your electrons, because when I get that double bond on, I don't need this set anymore because he's getting his electrons there. And I also don't need this set because he's getting his electrons. It's kind of like these have kind of come down. Now the question, shouldn't there be a resonance structure? Well, yeah, there should be. So here's the resonance structure. That's on the left-hand side. Fill in the electrons. Kind of got them a little close. I don't need any brackets for this one because it doesn't have a charge. And then you would also write a back and forth arrow between the structures. This is considered to have 1, 2, 3 regions. Anything with 3 regions is trigonal planar. Now look, we've got a lone pair, so our name changes. And this one's called bent. And the last example of something that has a resonance structure is right here. So this was our not correct answer on top. That was the not correct one. But the carbon, everything had single bonds and everything was all filled up. If you count them up, you get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, which is, of course, not 24. Means we are a difference of a pair of electrons, which is a double bond. And so this was the structure I drew right here. So we've got, if you want to double check, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that's all good with our electron counting. And then bracket, they should be vertical brackets, but these are kind of messy. That's 2 minus. This one needs a bracket, 2 minus, and this one needs a bracket, 2 minus. And you'll notice all I did was move that electron bond to there, that double bond, and then we also moved them to there. This shape has 1 region, 2 region, 3 regions. So 3 regions, which is trigonal planar. No lone pair, so he still has the same name, trigonal planar. And just to review linear, it's 180. Bent, it's 109.5, but it's a little bit less than that. And trigonal planar is 120. Just make sure I've said everything on this. I think that's the way we want it. The last thing that we did was we also filled in the resonance column. So like this guy, he had a resonance structure, so we checked him. This one was a resonance structure, so we checked him. And this one had a resonance structure, so we checked him. And if you want, go ahead and attempt to draw all of these. We're going to be finishing this up on Thursday. We're going to draw those structures. We're going to talk about polarity and flow motor charge. And then we're also going to touch on Chapter 5. And that should be the end of it.